Good evening, good morning, good afternoon, everybody. This is Sean Lally, your physics pal here, and today we're talking about conservation of momentum, or as you can probably tell by the moving image above, it's all about collisions. It's what happens when things undergo an event that we call a collision. It actually does not just apply to collisions, but it also applies to explosions, things that are moving apart, which is kind of the opposite of a collision if you think about it. So, let's get underway. All right, so to understand collisions, we do have to go back just a little bit. We've got to start thinking again, recall our friend Newton and Newton's second law. F equals ma. Another way to think of that is, of course, F equals m times the change in velocity per time. If we multiply both sides by t, we end up with Ft equals m delta v. Now, there's nothing too revolutionary about that. However, it does allow us to predict some pretty cool things, as we'll see in a moment. This expression is even sometimes given its own name, the impulse-momentum theorem, where we define impulse as something called F times the change in time, or just Ft if things happen to be constant. If the force is not constant, then the impulse is the area under the force versus time curve, which, if you are a calculus fan, you'd know that to be the integral of that function. So, excuse me. Okay, so let's talk about what this is all about, this impulse and momentum business. So if we take a look at this equation, force times time equals mass times change in velocity. What this is really saying is that an impulse that's delivered, a force times time, results in a change in some new quantity, mass times change in velocity, what Newton used to call the quantity of motion. We now call it momentum. So we're going to define this quantity, m times v, as momentum, and we represent it by the letter p, which actually comes from Italian, propella. It is a vector quantity, so it's directional. The units are kilogram meters per second. They could also be Newton seconds, which is the unit for impulse, if you prefer. But kilogram meter per second is the fairly standard unit for momentum, and Newton seconds is the fairly standard unit for impulse. So, what we now see is that during a collision, a force is imparted from one body to another, but this usually occurs during a very short time. If you've ever been in a collision before, you know that it might seem like a long time, but typically it's on the order of fractions of a second. Now, during this very short time, a change in momentum occurs for both bodies, or all bodies if there are more than two. So, we can also see that if no losses occur, then the quantities should be conserved. That is to say that if the impulse should be translated into a momentum, or another way to think about it is by saying the momentum before and after has to be exactly the same. This says a lot. If you think about how airbags work by sort of counterintuitively extending the amount of time that you're in contact with the airbag. It slows you down. It increases the time of contact, so you actually end up having a net smaller force delivered to you, and it saves your life. A boxing glove does the same thing. A boxing glove has padding on it so that when it makes contact with a person, then there's actually a greater amount of time of contact. Same thing for baseball gloves, so you don't get stung when you catch a high-speed baseball. It increases the time of contact. And on the other hand, why do eggs crack when they hit the ground? Well, they do that because the ground doesn't give way. The amount of time of contact is very, very small. So the force delivered to the egg is huge by comparison. Okay, here's an example of impulse and momentum in action. Let's consider a toy rocket car. This rocket car is propelled by an engine that delivers an impulse of 2.5 Newton seconds. Now, what that number represents is the product of force and time. This is a number that's typically shown on the engines that are sold commercially for vehicles like this. The amount of time is 0.8 seconds. The mass of the car is 86.25 grams, which is the average of pre- and post-launch masses, since it loses a little bit of mass of gas. And 2.5 Newton seconds is equal to the mass in kilograms times the change in velocity. So we should expect, with that amount of impulse, then the mass of that car should be propelled to a change in velocity of 29 meters per second, or about 60 miles per hour. So, conservation of momentum, our main topic. This does arise from Newton's third law. The equation we've just seen, Ft equals m delta v, works in both directions. Impulse causes a change in momentum, but momentum can be transferred from one body to another via an impulse. Now, the time span of collisions is usually small. It's very, very small. But we, upon examining the momentum before and after a collision, find that the total momentum is the same. This is a remarkably important idea, not just with conservation of energy, but conservation of momentum allows us to see how things move. We can even use this to see how star systems form and why the universe looks the way it does now. So during a collision, mathematically, the change in momentum from a vectorial point of view is zero, or if you prefer, in the sum of the initial momenta is equal to the sum of the final momentum. Momenta, plural. Here's some examples for you, kind of animated, but I want to show you what this looks like mathematically speaking. So you can kind of see what's going on here. When the masses are the same, kind of like billiard balls, so certain things can happen, but notice that the initial velocity and direction really does make a difference. So how do we calculate this? Turns out it's a little bit tricky. We're going to look at the classic one-dimensional collision problem, where we have the pink car or block on the left, m1, colliding with the blue or teal car on the right, m2. The initial velocities are v1i and v2i. Now, if we were recording these, we would say that one of these is positive and one of these is negative. Usually I say going to the right is positive and going to the left is negative in this case. So the sum of the initial momenta is m1 v1i plus m2 v2i. The sum of the final momenta is m1 v1f plus m2 v2f. There's a problem. You may know the masses and you may know their initial velocities, but that's not quite enough information here. Well, why? We set these equal to each other. That's one equation with two unknowns. We have two unknowns on the right side, v1f and v2f, so we have to have some other piece of information. And as it happens, we do. We know that kinetic energy is also conserved if this is what we refer to as an elastic collision. If this is an elastic collision, the kinetic energy is conserved. If you ever studied chemistry and you learned about the gas laws, then you know that what makes an ideal gas ideal is that energy, specifically kinetic energy, is conserved. So this is not unreasonable to assume in many collisions. Okay, so we can write another equation. Initial kinetic energy of the two bodies is equal to the sum of the final kinetic energies of the two bodies. Or if you prefer, you've got that longer expression down below, half m1 v1i squared plus half m2 v2i squared equals the sum of the final kinetic energies. Now, we actually have two equations and two unknowns. But man, oh man, there's a whole lot of algebra to do. We could, if you were so inclined, solve for v1f and v2f, but let's be honest, nobody wants to do that right now. So I'm going to give you the answers. There they are. This is the solution or solutions to the classic one-dimensional collision problem. The final velocity for body 1, v1 final, is given by that expression, and the one below it is the final velocity for body 2. Now, these are messy expressions. They truly are, but this is how you would solve it if you are dealing with two bodies both moving and colliding with each other. If they're moving in the same direction, then the initial velocities are both positive, especially if you could say they're going to the right. If they're moving in opposite directions, of course, one initial velocity is positive and the other is negative. Just be consistent in your use of a coordinate system. However, let's say that the second body is at rest. This sure makes the problem easier. So we find that if v2i goes to 0, that's when m1 is initially at rest, the problem looks a little bit simpler, and we end up with this expression. v1 final is equal to m1 minus m2 times v1i. All that divided by the quantity m1 plus m2. I apologize, that should be v1 final, not vi final. And v2 final is equal to 2 m1 v1i over quantity m1 plus m2. A good bit easier to solve. Watch the signs, they indicate the direction. If you're interested, do a search on omnicalculator.com for conservation of momentum, and this will allow you to make up and solve lots and lots of problems, or feel free to use it for your homework. Now, there are some general cases that are illustrated right here. You can see, I won't go through the calculations for these, but if one body is twice the mass of another and they collide with identical initial velocities, look what happens after. In the second case here, if you've ever played pool before, you probably have seen that case before. Two identical balls colliding, and one comes to a stop and the other continues on with the same velocity. If you're interested, you can run a simulation through PhET and change all sorts of different things, and you can run this as a lab. Of course, you're going to be forced to do a lab here shortly. That's your classic elastic collision shown on a Newton's cradle in this animated GIF. Now, inelastic collisions. Inelastic collisions are also quite important. Inelastic collisions are what happens when two things stick together or indeed explode apart. We still have conservation of momentum. However, unlike an elastic collision where kinetic energy is also conserved, in an inelastic collision, unfortunately, kinetic energy is not conserved. Some kinetic energy is going to be transferred into heat or some such, or maybe if they're sticking together with Velcro or something or magnets, then there's some energy that happens to be transferred there. And that's usually not that easy to quantify. We can calculate it after, but during the actual collision, it's not very easy to calculate the transfer of kinetic energy to some other form of energy. However, very conveniently, the momentum is still conserved during an inelastic collision. Take a look at this very quick animation right here. You go big fish, swallows little fish. They become one fish plus fish, big fish plus little fish, and they move on at a smaller velocity. Now, let me show you this. M1 V1I is colliding with M2, which is initially at rest. They collide and stick together. Then what happens is you have a brand new mass of M1 plus M2 moving at some new velocity V2 final. So, initial momentum equals the final momentum. M1 V1I is equal to the combined mass, M1 plus M2, times V2 final. Don't get hung up on the subscripts. I'm just using that subscript to indicate that they're moving together and with the velocity that is V2 final. We could put some numbers in here if we like. If M1 is 10 kilograms and V1I is 6 meters per second, M2 being 4 kilograms initially at rest, well, you can do the math, but it works out that the final velocity is 4.3 meters per second. Now, finally, our last topic for today is to talk about explosions, which also is a conservation of momentum concept. We have two bodies stuck together. Maybe they're held together with a spring, and kaboom! They actually explode apart. Well, in this case, with only two bodies to keep track of, it's not so hard. So, we can see that V1F is to the left, V2F is to the right. So the initial momentum of the system is 0, and that equals the sum of the final momenta. 0, initially, equals M1 V1F plus M2 V2F. One piece has to have a negative velocity. Now, of course, most explosions involve many pieces, not just two. But in 2 dimensions, we have to add angle. It gets a little bit trickier, but the idea is basically the same. We do, in fact, then break velocities into their respective components, and we deal with things in the x direction and things in the y direction. However, it's the same basic principle. Take a look at this. This is really worth checking out in greater detail. We have a car that is launching a ball backwards. I think I've shown you something like this before, but the car is moving to the left with a certain velocity and it moves the ball backwards with the same velocity, and the ball just drops straight down. I urge you to take a look at the full clip of this from Mythbusters, and you can look it up on IFL Science. And the topic is what happens when you fire a cannonball out the opposite way of a moving vehicle. That, my friends, is that. So, conservation of momentum, a truly important concept. It extends over all sorts of different areas of physics. To remind you, the initial momentum of the system equals the final momentum of a system. If it is an elastic collision, kinetic energy is also conserved. If it is an inelastic collision or an explosion, only momentum is conserved, though total energy is conserved. See you soon.